Hello everyone, I'm Paul and today we're solving problem 3350, adjacent increasing subarrays detection 2. This is a medium one with different possible solutions, and here I will show you what I think it's a very intuitive one. So let's start. If you haven't seen part 1 yet, I recommend you to go and watch that video first. It's in my channel. We are given an array nums, so let's say that we are given this. And we need to find two adjacent subarrays that are strictly increasing, and we need to find the maximum size for these two subarrays, considering that they need to have the same size. So we need to find k, and k is the size for these two subarrays. So for example, we could take this subarray and this subarray, and they are both strictly increasing, they are both adjacent, and the size of each of these is 2. So the result up to this moment is 2. But we can take these subarrays instead, this and this, and these are also strictly increasing, they are adjacent, and the size for each of these is 3. And given that 3 is greater than 2, and we need to return the maximum possible value of k, in this case we return 3. And there are different ways to solve this. For example, we could try every k from 1 to n divided by 2. And for example, here n is 8, n divided by 2 is 4. So we are trying subarrays of length 1, then subarrays of length 2, then length 3, then length 4. And we are checking every time if we can find two adjacent subarrays of each of these lengths that are strictly increasing. And if we can, we keep the maximum length, and that's the result. Now this is fine, but it's very inefficient. Why? Well, think about it. We can pick one of these sizes and try this size in this array. We are iterating this, then we pick another size, we iterate this again, then we pick another size, we iterate this again. So this is very inefficient. We need to think about something else. Now you could optimize this by running a binary search and using this as the low bound or left bound, and this as the high bound or right bound. And this is fine, but I want to show you another solution that I think it's very interesting. Let's say we have an array with all ones, and we are storing at each position the maximum size for a subarray that's strictly increasing and ends in the current index. Let's see what I mean. We start with all ones, and first we are here. Given that 5 is greater than 2, now the subarray, the maximum size for a subarray ending at this index that's strictly increasing is 2. How do we get 2? We take the previous value here, 1, and add 1. That's what we put here. So this is now 2. Now we are here. Given that 7 is greater than 5, we take this value and add 1. So we replace this with 3. And what this means is this is the largest subarray that's strictly increasing and ends at this index. Okay? Now let's say we continue and we are here. We are comparing this and this. Given that this is smaller than this, we keep 1 and continue. Now this is greater than this, so we take 1 plus 1 and we put 2 here. And this is greater than this, so here we put 3. So we'll call this end length, and we are doing exactly the same in reverse. We are calling this new array start length. And we are doing the same process from right to left. So we are here initially and we are comparing this and this. And given that this is smaller than this, we take this value, add 1, and put the result here. So this is now 2. And just to be clear, this 2 represents that the largest subarray that starts at this index and it's strictly increasing has length of 2. That's why here we have a 2. Now we are here, and given that this is smaller than this, we take this and add 1, so here we put a 3. Next here, given that this is greater than this, and we are going in reverse, we keep 1 here. And here we have all the information we need to solve this. We can iterate this once again from left to right, so the I pointer is initially here at index 0. And every time we are using this to split two subarrays. So from here, what's the largest subarray that's strictly increasing and ends at this index? Well, it's this subarray. Why? Well, because here we have a 1. And what's the strictly increasing longest subarray that starts at I plus 1, meaning here? Well, we go to this index, and we know that this has a size of 4, so this is the subarray. And remember that both subarrays need to have the same size. So we take the minimum among these two, and the minimum among 1 and 4 is 1. So we take this subarray and this subarray. The result is initially 1. Why 1? Well, because we will never have less than 2 elements in this array, and we can always pick subarrays of length 1. So the result is 1 initially. And now we are taking the maximum among 1 and 1. So we keep 1 here. Now the I pointer is here. So we are taking this subarray, meaning subarray that ends at this index. It has a length of 2. And we are taking the subarray that starts at I plus 1. It starts here. We know it has a length of 3, meaning we have these 3 elements in the second subarray. The minimum between these two is 2, so we are picking this second as a second subarray, and the result is the maximum between 1 and 2, so we replace this with 2. Next here we take a subarray of size 3, so we take this, and a subarray of size 2, we take this. The minimum between these two is 2, so we are actually taking these 2 subarrays. And the maximum between a length of 2 and 2 is 2, so we keep 2 in the result. Next here we have a 4, so we are taking this subarray, and here we have a 1, so we are taking this. The minimum between these two is 1, so we are taking these 2 subarrays, and 1 is more than 2, so we continue. Now here we have a subarray of length 5 to the left, so we have this, and to the right we have another one of length 3. The minimum between these two is 3, so we are taking this and this. And here k is 3, and the maximum between 3 and 2 is 3, so we replace this with 3. Now here we have a 1 and a 2 here, and the minimum here is 1. 1 is more than 3, so we continue. And finally here we have a subarray of length 2, and here we have another one of length 1. The minimum here is 1, so we are taking this, and the maximum between 1 and 3 is 3, so we keep 3 in the result. Now we update I, and we are out of numbers to build a second subarray, so we return 3. Time and space complexity for this approach will be big O of n. And with this in mind, let's go with the code, and hopefully you will get the idea. First we say n is the length of nums. And first we build the first array and length. Remember that every element in this array corresponds to the largest size for a subarray that's strictly increasing and ends at the corresponding index. So this is initially an array with 1 times n. And now for I in range from 1 to n, if nums I is strictly greater than nums I minus 1, and length at I is and length at I minus 1 plus 1. And we are doing exactly the same for start length. So this is an array with 1 times n, and for I in range from n minus 2 to minus 1 in steps of minus 1, if nonce I is smaller than nonce I plus 1, start length at I is start length at I plus 1 plus 1. So this is exactly the same, but we are going in reverse. Now we can build the result. So result is initially 1, and for I in range n minus 1, result is the maximum between the result and the minimum between n length at I and start length at I plus 1. Remember our drawing, this is exactly the same we did a few seconds ago. Finally, we can return result. So this is the entire code. Now let's submit this and see if it works. As you can see, this works and it's efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.